Hey everyone, and welcome to This Explainer. Today, we're diving straight into a rigorous, high-yield clinical review of something that has literally plagued humanity for millennia: gout and other crystal-associated arthropathies. Whether you're a clinical learner or just someone who's totally fascinated by the intricate ways our own metabolic pathways can suddenly trigger massive, agonizing inflammation, you are definitely in the right place. We're going to deeply analyze the pathogenesis, break down the precise clinical phases, look at the microscopic diagnostic clues, and finally, formulate targeted therapeutic management. Let's get started.
To really understand gout, we have to start with this absolutely fascinating evolutionary quirk. Have you ever stopped to wonder why we don't see our dogs or cats suffering from spontaneous gout? Well, it turns out humans suffered a species-wide evolutionary loss of an enzyme called uricase. In other mammals, uricase conveniently converts urate into a highly water-soluble compound called allantoin, which is easily cleared. But because we don't have it, humans are left with a naturally higher baseline of urate in our blood, and that leaves us uniquely vulnerable to hyperuricemia and the incredibly painful crystal formations that follow.
Okay, let's dive into this. Here is our roadmap for today. We're going to start with the pathogenesis of gout, track the clinical phases, head into the lab for synovial fluid analysis, identify other crystal arthropathies, and wrap up with therapeutic management. All right, Section 1, the pathogenesis of gout. So the absolute fundamental concept to grasp here is that chronic hyperuricemia, an increased body pool of urate, is the strict prerequisite for the disease. Basically, no hyperuricemia, no gout. But how exactly do we end up with all this excess urate? Well, on the left side we have overproduction, and this accounts for only about 10% of cases. This can be driven by increased cell turnover from things like psoriasis or malignancies, but it also includes some really fascinating inherited metabolic defects. For example, superactivity of the PRPP synthetase enzyme rapidly accelerates purine and urate production. Or take HPRT deficiency, which in its most severe form you might know as Leschner-Hand syndrome. In that scenario, a crucial salvage pathway is totally broken. Purines just can't be recycled, so they get exclusively dumped right into the urate production line. Now on the right side, we see the far more common culprit, which is underexcretion. This represents a whopping 90% of cases, and it's primarily driven by impaired clearance of urate through the renal proximal tubules.
Moving right along to Section 2, the clinical phases of gout.
Let's move to the bedside and see how this builds across a patient's lifespan in 3 very distinct steps. Step 1 is the acute flare. This is often an incredibly painful nighttime attack, and it frequently targets that first big toe, which is classically known as podagra. The joint gets violently red, hot, and swollen, often perfectly mimicking an infection like cellulitis. We actually call that pseudocellulitis. These flares can be triggered by purine-rich foods, a night of drinking alcohol, or ironically, even the initial introduction of urate-lowering drugs. Step 2 is the intercritical period. After a blazing flare finally resolves, the patient enters this completely asymptomatic, silent phase. But make no mistake, the underlying hyperuricemia is still there. If left untreated over the years, we hit Step 3, chronic tophaceous gout. This is a state of persistent low-grade synovitis where these growing crystal deposits called tophi create granulomatous inflammation, eventually leading to severe erosive bony deformities.
Next up, Section 3, synovial fluid analysis.
Now what's really interesting about this slide is that this is our ultimate diagnostic proving ground. Under a polarized light microscope, we can see the definitive visual signatures of these diseases. On the left side, we have monosodium urate, or MSU crystals, the classic hallmark of gout. Notice their really sharp, needle-like shape. Under compensated polarized light, they exhibit strong negative birefringence. In practical terms, that means they often appear brilliant yellow when they are aligned parallel to the axis of the compensator. Contrast that with what's on the right side, calcium pyrophosphate, or CPP crystals. These are the culprits behind pseudogout. They are distinctly rectangular, rod-shaped, or rhomboid, and they display weak, positive birefringence, so they often appear blue when aligned parallel. Spotting these precise optical differences in the lab is absolutely vital for nailing the correct diagnosis.
Jumping into Section 4, other crystal arthropathies.
Now, just when you think you have the diagnosis figured out, there are tricky mimickers to consider. These are highly specific yet easily missed crystalline villains. First up is calcium appetite deposition disease. This can cause acute inflammation, but it's really notorious for a chronic, severe, destructive arthropathy known as Milwaukee shoulder, which causes these massive hemorrhagic shoulder effusions in the elderly.
The catch here, these crystals are so incredibly tiny that they usually require electron microscopy just to spot them. On the other side, we have calcium oxalate deposition disease. This one is heavily contextual. You're almost exclusively going to see this in patients heavily dependent on long-term dialysis who have chronic renal failure. It's often linked to the ascorbic acid or vitamin C metabolic pathway, which breaks down into oxalate that their failing kidneys simply cannot clear.
And finally, Section 5, Therapeutic Management.
So the crucial point is that when formulating a treatment plan, you have to split your strategy into two totally different phases. Think of it as acute firefighting versus chronic prevention. When a patient is in the middle of an acute flare, your goal is purely to extinguish that massive fire. We use potent anti-inflammatories here, things like NSAIDs, colchicine, systemic or intra-articular glucocorticoids, and in severe cases, interleukin-1 inhibitors like anakinra. But, and this is super important, these drugs do absolutely nothing to reduce the body's overall urate burden. For chronic prevention, we have to pivot to urate-lowering therapies, or ULTs. We're talking about xanthine oxidase inhibitors like allopurinol and fubicostat to stop production, uricosurics like probenecid to increase renal excretion, or advanced biologic enzymes like pegloticase. These are the tools that actually fix the underlying metabolic defect.
And when you're utilizing those long-term therapies, this number is everything. Less than 5 to 6 milligrams per deciliter. That is the ultimate actionable clinical target for serum urate. Actually reaching and maintaining this subsaturation point is required not just to prevent future flares, but incredibly, to literally dissolve existing TOFI back into the bloodstream, completely reversing the crystal burden over time.
So we'll wrap up this explainer with a bit of a provocative thought. If chronic hyperuricemia is merely a baseline asymptomatic biochemical state for many people, sometimes lingering for decades, what exactly is the immunological tipping point? Like, what specific signal suddenly causes an inert, walled-off crystal deposit to shed into the joint space, triggering the NLRP3 inflammasome and unleashing one of the most painful inflammatory cascades known to human medicine? It's a great reminder that even though we can map out these metabolic pathways and target the crystals, the profound reactivity of our own innate immune system still holds some incredible mysteries. Thank you so much for joining me for this deep clinical dive. Keep exploring and keep learning.